Swayam Prabha. Digital India. Educated India.
Okay, so we talk about polynomial arithmetic. So we have seen for LFSR we have used something called primitive polynomial like 1 plus x to the power 4. So this type of polynomial we have seen in the LFSR, where LFSR 4-bit LFSR. So every LFSR is associated with a polynomial. So this polynomial is basically we have a connection over here and we have a connection over here. So this is the LFSR corresponding to this polynomial, and we have seen this LFSR is a good LFSR, good sequence generator, pseudo random number generator, because it gives us the full period and it satisfies some good statistical properties also. So we have seen this is a this is called primitive polynomial. So this is the today's lecture. We will talk about details about the polynomials, what is primitive polynomial, what is irreducible polynomials. So basically what is a polynomial? So a polynomial over an indeterminate x is a variable over an indeterminate x. So it is in terms of x, and it is over a, usually defined over a ring, but this is sometimes it is a field to have some properties of what is called Galois field. We will formally define the Galois field. So it is basically the expression like this: a0 plus a1x plus a2x square plus an x to the power n, this form, and this is denoted by f of x. So it is, this is called this expression is called a polynomial of degree n, provided this a n is not equal to 0. Okay, and these are called coefficient, this a0, a1, these are basically coming from some set, these are coming from say some field or some ring also. So polynomial can be defined over a ring. So these are the elements are coming from some ring, or it could be coming from some field for certain property to have. So we will formally define those. So let us go to the slide, please. So this is the expression for the polynomial. So any expression of this type is called polynomial, where this will be called n degree polynomial if a n is not equal to 0, and these are called a0, a1, a2, a n are called coefficient set, or these are called coefficient of the polynomial. So these coefficients are basically coming from some ring, or it could be come from some field. Okay. So now this polynomial will be called monic polynomial if the coefficient of a n is 1. So that means if this is 1, then it is called monic polynomial. So polynomial like this x to the power 5 plus x plus 2. So this is a monic polynomial because the coefficient corresponding to the highest degree is 1. So if a n is 1, then it is called monic polynomial. Okay. And n is the degree of this polynomial. So this is, and if the highest degree is 0, then this is basically a constant. Okay, so now let us take an example. Suppose n is 8, and suppose the polynomial coefficients are coming from 0, 1. So the coefficients are coming from 0, 1. So that is basically a f2. So if we take this polynomial where ai's are coming from f2, f2 is a field, this binary. So these are all binary bits. this A1, A2 all are binary bits. So, if you take this polynomial and we will see this particular form of this polynomial is say x to the power 8 plus x to the power 4 plus x 3 plus x square plus x plus 1. So, this polynomial is used in AES. When we will talk about the block cipher standard AES, advanced encryption standard, the Rindel, we will talk when we in a future talk lecture. So, there the designer used this polynomial. So, this polynomial is basically over F2, coefficients are basically 0 and 1, because coefficient of so this is basically 1 into x to the power 8 plus 0 into x to the power 7 plus 0 into x to the power 6 plus 0 into x to the power 5 plus 1 into x to the power 4, 1 into x cube plus 1 into x square plus 1 into x plus 1. So, these are the coefficient sets of this polynomial. So, this is a 8-degree polynomial. This is a irreducible polynomial. We will talk about what do we mean by irreducible polynomial. So, this is a irreducible polynomial of degree 8 over this F2. So, this is the polynomial, and this polynomial has important significance for us as it is used in AES standard. Okay. Okay. So, now for our cryptographic purpose, what we will do in this polynomial arithmetic. So, we will basically do the ordinary polynomial arithmetic, like how to add to polynomial, how to multiply to polynomial, how we can divide to polynomial like this. So, those are polynomial arithmetic, addition, multiplication, division. So, and also we will talk about polynomial arithmetic, but the coefficients are. So, here the ordinary polynomial arithmetic means the coefficients are the real number, it is coming from real number field. Now, the polynomial we will talk about for our cryptographic purpose over ZP. So, ZP means if P is a prime, ZP is the that 0 1 up to P minus 1. So, this is the residue class, this is the residue class. So, ZP. So, now we will our coefficients are coming from ZP. Then we will talk about a addition of 2 polynomial, multiplication of 2 polynomial over some polynomial which is mx, which is a irreducible polynomial. If you take, then it will form a group, that we will talk about this in more details. So, we take a polynomial mx, which is typically irreducible polynomial, like we have if this is mx, this polynomial. Okay. Then we will talk, we consider all polynomial mod mx basically. So, that set. So, we have to define those issues in our this polynomial arithmetic class. So, the coefficients are coming from ZP. So, in if P is 2, it is coming from Z2 0 1. Okay. Now, let us talk about ordinary polynomial addition. So, if we have 2 polynomial, say f x and g x, and if their degrees are different, say suppose we have so this is the ordinary polynomial addition. So, we have a polynomial f x, which is basically summation of a I x I is equal to 1 to n. So, this is basically a 0 plus a 1 x plus a 2 x square plus a n x to the power n. Can you please go to the board, please? So, then we have another polynomial g x, which is basically b I x to the power I is equal to 1 to m. So, this is basically b 0 plus b 1 x plus b n or b m x to the power m. So, 2 different degree polynomial. So, and these a i's b i's are coming from some ring or some field. This could be a ring or it could be a field. we need this to be a field to have that polynomial set that polynomial mod some irreducible polynomial to be a group, cyclic group. So, this is called Galois field. We will talk about that. So, the addition is simply the addition of the coefficient, because this. So, f x plus g x is basically a 0 plus b 0, a 1 plus b 1 x, like this. So, a I plus b I x to the power I. So, this plus is basically the field addition operation or the ring addition operation. So, in the ring or in the field we have two operations, addition and multiplication. So, there we can add two coefficient two element. So, these are the element coming from that ring or field. So, we can add this. So, this operation is basically operation in the that ring or the field. So, basically we are doing the addition over the coefficient. So, this is the basic addition operation. So, if you take, for example, if you take two polynomial, slide please. So, if you take two polynomial f x and g x. So, f x and g x. So, f x is basically x cube plus x square plus 2, this is this. Now, if you add these two, so x cube is the coefficient 1, there is no x cube. So, for x square we have coefficient 1 and here 1. So, it will give us 2, and for x there is no 1, there is minus 1. So, it is minus 1, then constant 1 a 0 b 0 is 2 and 1. So, it is 3. So, it is basically the addition of f x plus g x. Now, now we can similarly we can define the subtraction. Subtraction is basically we will just take the minus of g x. Minus of g x is basically we will take the minus of a i's of the coefficient, then we take the addition. Okay. And then the multiplication is basically if we want to multiply two polynomial, that f x g x. So, multiplication is basically we just take this into this. So, we first multiply. So, this is the simple multiplication operation. So, here x is just a symbol, it is the indeterminate variable. So, and all the operations will be over the coefficient. So, if we have two polynomials, say x cube plus x square plus 2, this is one polynomial. If you want to multiply this with another polynomial, x square minus x plus 1. Okay. So, this multiplication is simply we first take the x cube into x square minus x plus 1, then plus x square x plus 1, then plus 2 x square minus x plus 1. So, this will basically give us x to the power 5, this will give us x to the power 5 plus, and so here we need to do the addition operation over the ring or over the field. So, minus 2x plus 2. So, simple multiplication operation, and the degree will be basically degree of this polynomial plus degree of this polynomial. So, this is 5. Okay. So, the order or degree of the product polynomial is basically degree of the sum of their degree. Okay. So, now how to divide two polynomials? So, if you have two polynomials f x and g x, now suppose f x has degree more and g x has degree less. So, now we want to divide f x by g x. So, this is we know the real number division. So, if we want to divide say two real number, say okay. So, if you want to divide say 12 and 5. So, we have two real number, n is 12. So, a is say 12 and b is 5. So, how to divide two real number? So, a is 12, b is 5. So, we want to divide 12 by 5. So, 12 can be written as 2 into 5 by 5 plus 2. Okay. So, 12 can be written as 2 into 5 by 2. So, this 2 is basically quotient. So, this is basically a by b, this is basically 2 and this is the remainder. So, similarly for polynomial also, if we have two polynomial f x and g x, if the degree of f x is more. So, now we want to divide f x by g x. So, that means, so f x should be written as some q x g x plus r x, okay. And this r x is called remainder polynomial. And the degree of r x must be less than degree of g x, otherwise we have to divide again, and this is called quotient. So, then the degree of r x must be less than degree of g x. Okay. Now, if r x is 0, then we call g x divides f x. So, g x is a factor of f x. Then we say g x divides f x. That means, g x is a factor of f x. Okay. Now, we called a polynomial to be a irreducible polynomial if it has no factor. If such g x will not exist, then we call the polynomial will be an irreducible polynomial. For irreducible polynomial, it has no factor. So, we cannot reduce further. So, like this if we have say some polynomial x cube plus x square plus x, this polynomial is not irreducible polynomial, because this polynomial can be factored like this, x into x square plus x plus 1. So, this is not irreducible polynomial. So, there exists a g x such that it divides f x. So, a polynomial will be called irreducible polynomial if it has no factor. Okay. So, let us come back to the division. So, this is the division arithmetic for two polynomial f x and g x, and this q x is called quotient and this r x is called remainder polynomial. And okay. So, now we talk about Galois field or over the polynomial. So far okay, now for field operation we have seen there are some properties like these are the properties are there in the when we talk about field. So, these are the properties one it should obey for the set to be a field under these two operation plus and dot, and this field could be infinite. We have seen the real number field, set of real number with the usual addition and multiplication is a field, and it is an infinite field. But infinite field is not of our interest, because of we cannot take infinite number in a memory, our computer is finite memory. So, for memory is a limitation everything. So, we need to talk about finite field, that means the set on which we are talking about field should be finite, the number of elements should be finite in that set. So, how to get such finite field? So, we have seen the field like ZP. Now, we want to have a polynomial field. So, we have seen the ZP. ZP is basically 0, 1, 2 up to p minus 1. Okay. And Z2 is basically just the 0 and 1. Okay. Now, if you take a irreducible polynomial over Z2, say we have example of irreducible polynomial we have just seen, which we have used, which is used for AES. So, let us take that example. We can take another, there are many irreducible polynomials. So, suppose let us take a irreducible polynomial, the same irreducible polynomial we have Okay, so now let us consider all the polynomial which is basically z2x. z2x is basically, this is the set of all polynomials, summation of ai xi to the power I, yes, I is from 0 to n could be anything. So, where ai's are coming from z2. Okay. So, suppose we take, all possible polynomial whose coefficients are basically 0, 1 and which is of any degree. So, this is one polynomial 1 plus x, 1 plus x square plus x to the power 10, 1 plus x to the power 9, x to the power 101, like this, any such polynomial, but the coefficient must be coming from z2. So, that set is denoted by z2x. Okay. This is the set of all polynomial whose of any degree whose coefficients are basically the binary bits. Now, we take the modular of irreducible modular of this polynomial. So, we take z2x mx. So, this set is basically, so we take any arbitrary polynomial of any arbitrary degree, then we try to divide that with this irreducible polynomial. So, then the degree of that polynomial of the remainder, then the remainder will be of degrees maximum 7. Okay. So, this will be the set of all polynomial whose degree is like this, b0 plus b1x plus b2x square up to, this is from 0. So, b1x, so b7 x to the power 7, where bi's are coming from 0 and 1. Okay. So, this set. So, basically the idea is we take a arbitrary polynomial of any degree, then we try to divide that polynomial with this degree. So, if you take any arbitrary polynomial of any degree, so if you try to divide by this, then we will get some quotient and some remainder, and that remainder is basically mod of that polynomial fx mod mx. This remainder polynomial is the mod of that polynomial, because that is the remainder polynomial, and since the mx degree of mx is 8, so the degree of this remainder polynomial will be maximum degree 7, otherwise we have to divide again. Okay. So, now if we consider this polynomial, and it can be shown that this polynomial will form a field under polynomial addition and multiplication, and this, so this polynomial set, so this we denote by say gf, this is gf2 basically 2 to the power 2, or we can just anyway, this is called Galva field. So, sorry, gf 2 to the power 8, because what is the number of element. So, if this is the set S or G set, okay, now what is the cardinality of G set? Cardinality of G set is all possible values of this b0 and b1. So, there are two possibilities, 2 to the power 8. So, this is a finite set, and we can show that G with the this plus and multiplication, and this plus is basically, if you take any two element fx and gx from this set G, this plus is basically gx. So, this polynomial plus mod that mx. Okay. This is how we define this plus. So, that means we take any two polynomial of degree 7, we add it up and then we take the mod, and similarly. So, this is under modular operation of mx. So, polynomial modular operation of 7. Now, so this is again similarly multiplication is also same under the modular operation. So, if we take two polynomial f x and g x, f x into g x is basically the polynomial multiplication mod m x. Okay. So, it can be shown that this is a field. This is a field. So, this field is called finite field because the number of element is finite. So, this is also called Galois field. So, this is called Galois field. So, this is coming from the irreducible polynomial. So, we have to choose a irreducible polynomial, and then irreducible polynomial is also called prime polynomial because it has no factor other than 1 and m x, because it cannot be reduced further. So, that means in the prime number we know if a number is prime, that means it has only one, it has two factor 1 and itself. So, that means similarly for m x also it has only it has no factor. So, that means, so this is also called prime polynomial, not primitive polynomial. We will define primitive polynomial. So, this is the this is called Galois field of 2 to the power, sorry, this is 2 to the power 3 because this is 8 2 to the power 3, that is 8. So, this is called GF 2 to the power 3. So, instead of Z2 we can take ZP also, where P is a prime. Okay. Then it will be general group of GFP. So, this is the so we take P to be prime in order to have this group. So, these are the operations over this. This is just to recall to have the group. This is the modular operation over mod n. So, here we are choosing n to be pre. Okay. So, now this is this under these two operations we have already talked about this. So, this is forming the group. Now, how to define a primitive polynomial? So, we know the Galois field. So, it is a group under both multiplication and the addition. Now, a polynomial is called a primitive polynomial if it is a generator of that cyclic group. If it is a generator or the primitive element, generator is also called primitive element. Of the group that Galois field, I mean 2 to the power 3 say. In general it is 2 to the power GFP. So, this is a group. So, this G, so it is a group under multiplication also. So, it is a cyclic group. So, if we take a polynomial say Px, it will be a, so first of all it has to be irreducible polynomial. So, every primitive polynomial is a irreducible polynomial. On top of that, it should have a extra property that it should be the generator of that group. So, it should generate the group G in the multiplicative sense. So, this is a primitive polynomial, and we have seen this primitive polynomial in the context of LFSR. Thank you.